All right, in this video, we're going to talk about extrema. We're going to talk about relative extrema and an absolute extrema. So we're going to talk about the highest point, the lowest point on the graph, and then we're going to talk about relative max, relative min, which is going to be the highest and lowest point within a certain area of the graph. So if you look at this graph here, well, first off, if you look at this graph here, we'll call this graph 1, graph 2. They're similar. Okay, the top one is on an open interval. The bottom one is on a closed interval. So let's address the closed interval first. So with a closed interval, you're always going to have an absolute max, and you're always going to have an absolute min. So on this graph, this is going to be my absolute max. This is going to be my absolute min, because it's the lowest point on the graph. This is what we'd call a relative max, and this is a relative min. Now, the one up here is on the open interval. So this, technically we can call this an absolute max and absolute min, but from my experience with the AP exam, when you're on an open interval, that we're just asking for relative max, relative min. So this would be relative max, relative min. So what I want you to notice is that at each of these relative max or mins, the slope is 0. So we can draw tangent lines like this. And at each of these tangent lines, the slope is equal to 0. So slope is 0, slope is 0, 0, and slope is 0. Okay? So if you look at graph number 2, what would be the process? Well, we would first want to find the relative max and the relative min. So we would set f prime equal to 0. We'd figure out where that x value is, so x equals some number. And then we're going to go back to the original function and plug in all the x values. So we would plug in this x value, this x value. We're also going to plug in the endpoints. So you must test the endpoints. And then we take a look at all the y values, see which one's the highest, see which one's the lowest. That would give us our absolute max, absolute min. Okay, here, I don't want to spend too much time here because this is chapter 3.3, where we do relative max and mins. But again, you're going to do f prime equal to 0, and then we're going to do a certain test to see if it's a relative max or a relative min. Okay? And it has to do with the behavior of the graph around it. So if it's going from increasing to decreasing, then I know it's a maximum. If it's going from decreasing to increasing, it is a minimum. But again, we'll address that in chapter 3.3. So with an open interval, we're basically looking for relative max or mins. For a closed interval, you always want to consider the endpoints. Okay, so for this, we use a lot with the word problems. So word problems. Specifically the rate problems, because we'll talk about the rate entering, or let's say you're online, you're going up an escalator, or the line to get on to something. A lot of times, the most amount of people is at the beginning or at the end. So sometimes it's here, and sometimes it's here. So we always want to consider the endpoints on a closed interval. Now, if you look over here at this graph, it's on a closed interval. So my endpoints I would have to check. Now this is a relative min, a relative max. So relative max, relative min. This is actually the absolute minimum point because it's the lowest point on the graph. So this point actually comes lower than the endpoint. So I drew this kind of funky to show you that it's not just where f prime equals 0, but it's where f prime is undefined. Okay, and we'll talk about that as we work through it. So these are all called, also too, they're critical numbers. So critical numbers are going to be where f prime equals 0 or f prime is undefined. So not every critical number becomes an extrema, but every extrema is a critical number. Okay, so you could have a graph that maybe something like this. Think of, let's say a graph like that. So if we're looking at the slope here the slope is 0 here. It's an x-cubed graph. So the y prime, where the slope would be 3x squared. If we did 3x squared equal to 0, we would get x equals 0. So at 0, so that's a critical number because f prime equals 0 at 0. But it's not a maximum or minimum. It doesn't really change direction, right? It thinks about it. It's going up. It's not coming this way. If it came this way, then it would be a relative maximum. But it's going up and then it's continuing upwards. So this actually has no maximum or no minimum. So not every critical number becomes an extrema. All right, let's work through these examples here. So we want to focus on, basically, the trick to this is just starting to learn like the closed interval, closed open, open open, and closed closed. Okay, that's going to dictate whether or not we get not critical numbers, but absolute extrema. All right, so for the first one, we've got -4 to 0, so absolute max at x equals -2, and the absolute max equals 2. So that's the value of it, okay? The absolute min, because it's on a closed interval, it's going to be at the nth point, so it's going to be at x equals -4, x equals 0, and the absolute min is equal to 0. All right, here we're going from -2 to 0. So the absolute max is at x equals, so at x equals -2, and absolute max is 2. And then absolute minimum, there is none. Because we're going from here and then to here, but it's on an open interval. All right, for part C, we're on the open interval the whole time. So, and we're going from -4 to -2. All right, so we're only going from here to here. Since these are both open and open, there would be no absolute max and no absolute min. So there's no absolute max and no absolute minimum. All right, then the last one, we've got -4 to 0, closed interval to open interval. So absolute max, there would be none. And then absolute minimum would be here at -4. So at x equals -4, and the absolute max equals 0. All right, so what do things need to be in the case for there to be both a max and min for the graphs in example 1? So, well, first it needs to be continuous on a closed interval. All right, so extreme value theorem. So this is abbreviated EVT. And it says if f is continuous on a closed interval, that's the key to this, closed interval, then there has to be both a maximum and a minimum on that interval. All right, so we've talked about relative max, relative min. Okay, so that's going to be within a certain area of the graph. So when I look at this graph down here, this is a relative max, this is a relative min, this is a relative min, okay? Now it's saying what is the value of the derivative at each of these relative extremas. So the slope is 0. So remember, the derivative is the slope. So slope equals 0. In this case, slope is undefined. But it's still continuous, and that is still a relative min. All right, so for the first graph, the relative extrema would be at 0, 0. So the relative min is at 0, 0, and the relative max at 0, 0. And the relative min is at 2, negative 4. So 2, negative 4. And the one over here on the right, the relative min is at 1, 0. All right, so definition of a critical point. So we sort of talked about it. So the critical point is when f prime is equal to 0 or f prime is undefined. So relative extrema only occur at critical points. So that means, so your relative extrema are the ones in between, right? So it's not on the endpoints, it's in between. It can only occur if the slope is equal to 0 or the slope is undefined. I mean, you can have, the obvious is like your parabola type graph. So these are all relative extrema, right? The slope is 0, slope is 0, slope is 0. You could have a graph that looks like this, maybe. So we have a cusp here. It would not be differentiable at that point, but it's still a minimum point on the graph. So this would be a relative minimum point. So f prime is undefined. This would be f prime equals 0. So for this to occur, one of those things have to happen. Either slope is equal to 0 or the slope is undefined. All right, so this would be a relative maximum. This would be a relative min. And this would be a relative max. And this would be a case where the slope is undefined. It looks like maybe a vertical tangent line, a cusp. But this is where f prime equals 0. F prime equals 0. F prime equals undefined. So something you could think about would be something like this. Let's say we had y equals x to the 1/3 power. So that is this, so cube root of x. So let's look at this graph for a second. So it's a continuous graph, right? Because you could take the cube root of anything. So it looks like this, and it looks like that. So that's the graph of the cube root of x. So it's continuous. There's not a domain restriction on this graph. But when you derive it, watch, we get y prime, you're going to get 1/3 x to the negative 2/3. So y prime equals 1/3, and then we'll just say x to the 2/3 power. So now we have a restriction in the derivative. There was no restriction here. There was no fraction, right? But now the x went to the bottom, so x cannot be equal to 0. So at x equals 0, the derivative is undefined. So if you look at this graph, there's a vertical tangent line here at 0. All right, so let's work through actually finding absolute extrema on a closed interval. So you will always get an absolute max or min question on the AP exam. They always ask it. Sometimes not explicitly. You have to notice that it's on a closed interval, which implies you're checking the endpoints, but you always on a multiple choice question. And I'll be honest with you, most of the time it comes from an endpoint. And the reason it comes from an endpoint is because a lot of the times the functions are something like this. And use common sense here, but if you had something like this, and even if you derive it and you come up with the points you go to plug in, usually the highest or lowest point occurs at the endpoints because those are the smallest or largest numbers, right? So if we went on the interval 0 to 5, let's say we get critical numbers between. So they're going to be between these two. But more often than not, when you plug into the original function, this or this, being the smallest number or the biggest number, is going to give you the smallest value or the largest value, because you're cubing a number, you're squaring a number, and so forth and so on. You still need to check. But you'll see when we do the multiple choice, a lot of times I feel that you could say, you know what, it's going to come from an endpoint. Just look at the function, okay? All right, so let's go through this. So the first thing we want to do here is find the derivative. So step 1 is going to be to find the derivative. So find f prime. We're going to set f prime equal to 0, and then we're just going to do a xy chart. That includes the endpoints. All right, so let's go through this. So we have f prime of x. So we're going to get 12x cubed minus 12x squared. So f prime of x, I'm going to take out 12x squared. I'm left with x minus 1. We get x equals 0, x equals 1. So those are my two critical, so these are critical numbers. I don't know that they're max or mins. So critical numbers. So I'm going to do a little XY chart. And we're basically going to test the critical numbers and the endpoints. So I'm going to go from -1, I like to go low to high, then to 0, then to 1, then to 2. And I'm literally just doing an XY chart. When you do an XY chart, you go back to the original function. So if I plug in 0, we get the 0. If I plug in -1, you get 3 plus 4, I believe. You get 7. If you plug in 1, you get 3 minus 4, you get -1, and then you get 16. All right, so that makes my absolute maximum at 2, 16, and the absolute minimum at 1, -1. All right, this one, find the extrema. So again, these are closed intervals, so we want to consider the endpoints here. So we're going to start with, so this is something that I was talking about. So, and I really think is you need to graph this on Desmos. This is one you definitely want to graph on Desmos. Because this is a continuous function. There's no restrictions, there's no fractions, there's no vertical asymptotes. It's a continuous function. But you're going to see that the derivative it's not differentiable. At some points, you're going to see here in a second, we're going to get a 0 on the bottom of a fraction. So it probably means there's some sort of a cusp in the graph. In the graph, you're going to get some sort of something like this, I think, like that. But let's do it. So we're going to start with f prime. So f prime of x is equal to 2 minus, so 2/3 times 3 is just 2. So 2x to the -1/3. So this is why the derivative becomes undefined, because now you have an asymptote in the derivative. So we're going to get f prime. So 2 minus 2 over the cube root of x. You're going to set it equal to 0. So 2 minus 2 over the cube root of x. All right, so to solve this, we're going to get 2 equals 2 over cube root of x. I'm going to flip-flop these two like that. So cube root of x is 1, so x equals 1. So when x equals 1, f prime equals 0. So this is a critical number. Okay, so I have my critical number. I'm going to have my endpoints. But there's also where it's undefined. So I'd set the bottom equal to 0. So cube root of x equals 0 at x equals 0. So that's also a critical number. So x equals 0 because f prime does not exist. So again, it's just to go back to the original function, it's continuous over the entire domain. So there's no holes, jumps, gaps, vertical asymptotes. But when I derive it, because my exponent becomes negative, it puts me to the bottom of a fraction, which is going to give me an undefined point in the derivative, okay? All right, so I'm going to just test. I'm going to go just do an XY chart. So I've got, what do we come up with? We got 0, 1. So we start with -1, 0, 1, and 3. And I'm literally just doing an XY chart, plugging back to the original, see what heights I get for each of these points. So I believe this is -5, 0, -1, and I did this with a calculator to get -2.41. So my absolute min is going to be at -1, -5, and then the absolute max is going to be at 0, 0. All right, find the absolute extrema. I actually thought we were going to get a domain restriction, but we don't. So one thing you want to think about, let me address this real quick, is please make a note of this. Let's say we had f of x equals 2x over x minus 1. So x, there's a vertical asymptote at x equals 1, so it's not continuous. So when you do a derivative, you're going to see a first derivative, second, third derivative. This is going to remain in the denominator the entire time. So you're still going to get x minus 1 in the bottom. Watch, because we get this. Low, d high, minus high, d low, all over the bottom squared. So you're never going to lose that x minus 1 as you do your derivatives here. So when we set f prime equal to 0, right, we set f prime equal to 0, we set f prime equal to undefined. So x minus 1 equals 0, x equals 1. So that's where f prime is undefined. This is not a critical number. It's not a critical number because it's not in the domain of the function. It's still an important point, so you still want to find that point, because you're going to see when we do this, we're interested in the behavior of the graph around this point. So like, for example, so this is at what? At 1? So yeah, it's a vertical asymptote. But it's important to make note of that because I want to know what the graph is doing to the left of it, to the right of it. Maybe it's going this way, maybe it's going that way. So it's technically, well, not technically, it is not a critical number, but it's still very important, okay? All right, so that's what's different about this one. So like I saw the fraction, I'm thinking, but there's no domain restriction here. Okay, there is no domain restriction because the bottom, even though if you set equal to 0, you're going to get an imaginary number. So we're just going to do f prime. So I'm going to actually skip over the quotient rule and just get to the answer. So you would do quotient rule for this. Low d high, high d low, bottom squared. So you get -2x squared plus 2, and then x squared plus 1 squared. So that is the first derivative. So we're going to set f prime equal to 0. So f prime equal to 0. So you could actually just set the top equal to 0. So we're going to do -2x squared plus 2 equals 0. So I get 2x squared equals 2, x squared equals 1, x is plus or minus 1. And then the bottom, it still remains the same. You set the bottom equal to 0, but we're going to get an I here. So we can disregard it. But we knew that. So we're really just looking at where it's equal to 0. So that's 1 and -1. I'm going to do my XY chart. So I'm going to start with the endpoints of -2, -1, 1, and 2. And again, because you're just doing Like this is 7th grade math here, right? You're just plugging in points to get the height of the graph. It's like you were actually trying to create the graph. You have the x value, you plug in to get the y value. So this is negative 4 over 5. This is negative 1, 1, and 4 over 5. All right, so the absolute min is at negative 1, negative 1, and then the absolute max is at 1, 1. Okay. All right, last one here. It's a continuous function, so I don't have to worry about anything I find are my critical numbers, okay? So we have f prime is equal to, so it's 2 cosine of x plus 2 sine of 2x so f prime of x is equal to 2 cosine of x plus, so I'm going to use a double angle formula here. So the sine of 2x, I can rewrite it as 4 cosine of x sine of x. So now I can just go ahead and factor. So we're going to take set equal to 0, so 2 cosine of x, then it's 1 plus 2 sine of x. Set them both equal to 0, so 2 cosine x equals 0, 1 plus 2 sine of x equals 0. Cosine x is 0, so that's going to be at, I'm thinking of the graph, the cosine graph in my head. That's how I like to do it. So I'm looking at pi over 2. So it goes like this. So we're looking at there and there. So x equals pi over 2, 3 pi over 2. And then sine x equals negative 1/2. So we're looking at 30, but we're looking at third and fourth quadrant. So x equals 7 pi over 6, and then 11 pi over 6. All right, so XY chart. So we're going to start with 0, and then we've got pi over 2, 7 pi over 6, 3 pi over 2, 11 pi over 6, and then 2 pi. All right, and again, just for time, I'm going to give you the answers here, but you're just going to plug in. You plug back to the original, so plug into original. So at 0, it's negative 1. At pi over 2, it's 3. Negative 3 halves. Negative 1. Negative 3 halves. And negative 1. So my max is at, so pi over 2, 3. That's that one. And then my minimum are at the negative 1s. No. It should be at 7 pi over 6. So it's here. At the negative 3 halves. So the minimum, absolute minimum, would be at 7 pi over 6, negative 3 halves. And then 11 pi over 6, negative 3 halves.